Hello? Oh, we're a bit tilted, aren't we? What the heck? Okay, so today we're actually going to finally get into the logarithmic forms for a few of the inverse trig and inverse hyperbolic functions. So I'm just going to do like 2, maybe 3 from each, and then I'm going to leave the rest as an assignment if you want to do that. I've never assigned homework before, but here's to starting a new tradition, right? Getting the audience involved. And it won't be too hard, and what we're going to do is we're going to use the forms that we derive in a very interesting follow-up video involving a very fun constant, or a very sort of surprising constant, that comes from the fact that all parabolas are actually similar shapes, just like all circles are similar to each other, even though parabolas are infinitely large. And it's going to involve things that we derive in this video. So, let's get to it. Let's merge logarithms with our trigonometric world. Okay, so we're going to start off with the inverse hyperbolic sine function, and then we're going to work our way through there. I've got 5 little demonstrations that I want to do for this video, so we're going to try and find a closed form version of y equals the inverse hyperbolic sine of x, right? So in order to do this, we're essentially going to solve for y in a different form. So what we're going to do is we're going to take the hyperbolic sine of both sides. So we get that the hyperbolic sine of y is equal to, now what happens when you take a function applied to its inverse? Well, they cancel and you just get the input back. So essentially we've got the hyperbolic sine of the inverse hyperbolic sine of x, which is just equal to x, right? But we know what the hyperbolic sine of something is equal to, right? From its definition, we know that this is equal to e to the y minus e to the negative y all over 2, right? That's what the hyperbolic sine of y is. So in this form, with this equality, we can now solve for y in a nice closed form, which will involve logarithms. So we're going to multiply the 2 over, and we get that 2x is equal to e to the y minus e to the negative y. Well, I actually want to try and get this in a particular form, so what I'm going to do is I'm going to multiply through on both sides by e to the y. So this implies that 2 times x times e to the y is equal to e to the 2y minus 1, right? Because multiplying this by e to the y is like multiplying reciprocals, and so you just get 1. Now I'm going to subtract this term over, and you're going to see that we're going to have a very interesting form. So I'm going to write this as e to the y squared, because that's what it is. And we're going to have minus 2x times e to the y minus 1 equals 0. Now, what you can see is that we have something squared minus something times that thing that we squared minus 1 equals 0. This is just a quadratic equation in e to the y. So we can solve for e to the y by using the quadratic formula. So we know that e to the y will be equal to negative b, or positive 2x, plus or minus the square root of 2x squared, which is 4x squared, minus 4 times a times c. So 4 times 1 times negative 1. So minus negative 4, so plus 4, all over 2a, and a is 1, so we divide by 2. Now, this factor of 4 inside the radical can be factored out as 2 on the outside of the radical because the square root of 4 is 2. So this can be rewritten as 2x over 2, which just becomes x, plus or minus 2 times the square root of x squared plus 1, but 2 divided by 2 again gives 1, so we just get x plus or minus the square root of x squared plus 1. But this is e to the y. We just want y, which tells us that if we simply take the natural logarithm of both sides to cancel the e to the y, we get that y is equal to the natural logarithm of x plus or minus the square root of x squared plus 1. And what is y? Y is the inverse hyperbolic sine of x. So this is the natural logarithm form of the inverse hyperbolic sine. And so now we're going to do the inverse regular sine just to see the analogous form of it. So I hope that's very clear how we did that. If you plug this into Desmos and then this into Desmos, you get the exact same function. So here we go. As I said in the by the way, as I said in the graphing video of the inverse hyperbolic functions, I did say the inverse hyperbolic sine grows logarithmically, which is exactly what it does, right? Because the square root of x squared is going to grow like x. So this thing in here is going to grow probably something like 2x, and so it's going to grow logarithmically, very simply. So now we're going to do the inverse sine function. which just has a slightly different definition, right? So we're simply going to take the sine of both sides. Again, the inverse functions will cancel, so we get the sine of y is equal to x, and then using the definition of the sine that you get from Euler's formula, we have that e to the iy minus e to the negative iy over 2I is equal to x. And all we're going to do is do the exact same steps. We're going to multiply 2I over, multiply through by e to the iy, combine all the like terms together, and use the quadratic formula. The only difference is that we've got a factor of I, but I is just a number, right? We can treat it as such, and there's no difference. Multiply 2I over, we get 2I equals, 2ix, my mistake, 2ix equals e to the iy minus e to the negative iy, multiply through by e to the iy and subtract that term over, and we get e to the iy squared minus 2ix times e to the iy minus 1 equals 0. So again, we simply do the quadratic formula, and we get that e to the iy is equal to 2ix plus or minus the square root of negative 2ix squared minus 4 times 1 times negative 1, so plus 4, all over 2 times 1, which is 2. So again, the 2's cancel, and we're left with I times x, and the negative I squared is negative 1, 2 squared is 4, so we can factor out the 4, and that's going to be a 2 on the outside of the radical, which is again going to cancel with the 2 in the denominator, and we're just going to end up with plus or minus the square root of 1 minus x squared. And simply we're going to take the natural logarithm of both sides again, and then we end up with iy is equal to the natural logarithm of ix plus or minus the square root of 1 minus x squared. Of course, we want to solve for y, not I times y, so we simply divide by I, but as we know from complex numbers, that 1 divided by I is the same as negative I. So the logarithmic form for the inverse sine is actually a complex logarithmic form. So it's equal to y equals the inverse sine of x is also equal to negative I times the natural logarithm of the quantity of I times x plus or minus the square root of 1 minus x squared. So there's that. I'm going to do now the hyperbolic cosine. So I hope that's clear. It's very lovely. It's a lovely little formula. And if you plug in values that are real numbers between negative 1 and 1, that formula will give you the real values that the inverse sine function does. So it's actually quite cool that it can be written in terms of these complex numbers, yet it still gives real values over its normal domain. Now, we're going to do one more of these because it's something that I'm going to mention in the next video. So we have y equals the inverse hyperbolic cosine of x. So we're going to just do the same thing, and we get that the hyperbolic cosine of y is equal to x, and using the definition of the hyperbolic cosine, we have e to the y plus e to the minus y all over 2. And we're going to solve it in the exact same way. So we get that 2x is equal to e to the y plus e to the minus y, which tells me that e to the y squared minus 2x times e to the y plus 1 equals 0, right? I'm just multiplying through by e to the y and moving everything to one side of the equation, which tells me that e to the y is equal to, we're going to end up with x plus or minus the square root x squared minus 1. Simply taking the logarithm of both sides, we get that y is equal to the natural logarithm of x plus or minus the square root of x squared minus 1. Very lovely little formula, and this is for the inverse hyperbolic cosine. So I've shown you three. I've shown you the inverse sine, inverse hyperbolic sine, and inverse hyperbolic cosine. I'm going to show you one more in two different ways. What I'm going to show you is how to derive the inverse tangent from this setup, and then I'm going to show you how to derive the same thing, but in a more calculus-y way. So we're going to now investigate the inverse tangent, the regular inverse tangent, right, not the hyperbolic one. So we have y equals the inverse tangent of x, which tells me that the tangent of y is equal to x, which again, using the definition of the tangent, which we get from using the definitions of sine and cosine from Euler's formula, we get that this is equal to e to the iy minus e to the negative iy over 2I, which is the sine function, divided by cosine, or multiplied by the secant function, which is 2 divided by e to the iy plus e to the minus iy. Right? This is just 1 over the cosine by definition. Simplifying, we end up with x is equal to e to the iy minus e to the negative iy all over e to the iy plus e to the negative iy times I in the denominator, right? Because the 2's will simply cancel. So this is the definition of the tangent of y, and we're simply going to solve it in the exact same way. I'm going to multiply the top and bottom by e to the iy so that we get the quadratic terms that we want. And so this is going to be equal to e to the 2iy, and I'm going to multiply the I over to x, right? So we're going to get that I times x is equal to e to the 2iy minus 1 divided by e to the 2iy plus 1. Very simple, right? And now what we're going to do is we're simply going to multiply that term over, distribute things together, and then combine like terms. So we're going to end up with I times x times e to the 2iy plus I times x equals e to the 2iy minus 1. So now I'm going to simply combine these two like terms together, and I'm going to subtract that, I'm going to subtract this term over and then add the 1 over. So we get that 1 plus I times x is equal to e to the 2iy times 1 minus ix. Right? Simple as that. We're going to divide by this term and then take the natural logarithm of both sides. So we get that 2iy is equal to the natural logarithm of 1 plus ix divided by 1 minus ix. So you could do this as the difference of the logarithms, but I'm just writing it as one term. Divide by 2i, and you get that y is equal to negative I over 2. Distributing that negative 1 in, we can actually reciprocate this, so we can simplify it. So when you distribute the negative 1 into the natural logarithm, that's like raising the argument to the negative 1 power. So we're essentially going to have the reciprocal. So we have 1 minus ix divided by 1 plus ix. This can theoretically be simplified even further by simply multiplying the top and bottom of the argument in the logarithm by I, and we get that it's equal to I over 2 times the natural logarithm of I plus x. Right, multiplying through by I get I minus I squared x, which is minus negative x, which is plus x, divided by I minus x, right? Which I think is a nicer, even prettier way of writing it. So this is the natural logarithm form of the inverse tangent, and the reason I did this is because I want to show you how you can get the exact same thing by sort of applying complex numbers to a well-known calculus fact. So this is the inverse tangent of x in terms of natural logarithms and complex numbers. Very, very pretty, very, very beautiful. If you plug in any real number, you're going to get exactly what you get with the tangent, the inverse tangent function as you are familiar with it. So what we're going to do now is derive the exact same result using a slightly more calculus-y version. So we understand from our basic calculus classes that the inverse tangent function is an antiderivative of 1 over 1 plus x squared. So the inverse tangent of x is equal to the integral from 0 to x of dt over 1 plus t squared. And what we can do is write 1 plus t squared like this. So we have the integral from 0 to x of dt over 1 minus negative t squared. This is now a difference of squares, so we can factor it as such, and we get the integral from 0 to x of dt over 1 plus it times 1 minus it. And now all we're going to do is use partial fractions to split this up into its two parts. So what we want to do is we want to write 1 over 1 plus it times 1 minus it as equal to some number divided by 1 plus it plus some other number divided by 1 minus it. And that's quite simple to do. We're essentially going to multiply through by both of these things and set that equal to 1 and simply combine like terms. So we're going to get that 1 is equal to a times 1 minus it plus b times 1 plus it, which is equal to a plus b plus it times b minus a. Because this is just 1, that means the linear term has to be 0, not to mention the imaginary part of the term has to be 0. So b minus a has to be 0, which means b has to equal a. We know that a plus b has to equal 1, so a and b must both be 1/2, which means that our integral is now going to be equal to the integral from 0 to x of 1/2 times 1 over 1 plus it plus 1 over 1 minus it dt. And now the natural logarithm is going to be the answer for both of these things, but we just have to also then divide by the derivative of these things. So we end up with 1/2 times 1 over I, which is negative I, times the natural logarithm of 1 plus it plus 1 over negative I, which is I, times the natural logarithm of 1 minus it. We can factor out I, and we end up with this natural logarithm minus that natural logarithm, which means we can divide the natural logarithms together, and we get I over 2 times the natural logarithm of 1 minus it divided by 1 plus it, which is exactly what we derived before. If you multiply inside by I on the top and bottom, you'll get the exact same result. And so we've shown that this result can be derived from calculus and integral calculus specifically, as well as simply using the facts that we know about inverse functions. So now that I've shown you all of these neat examples of finding the natural logarithm forms of the trigonometric and hyperbolic inverse functions, these are the ones that we haven't done yet. So we didn't do the inverse hyperbolic tangent of x, the inverse hyperbolic cosecant of x, the inverse hyperbolic secant of x, the inverse hyperbolic cotangent of x. As well, we did not do the inverse cosine of x, the inverse cosecant of x, the inverse secant of x, the inverse cotangent of x. We did the inverse hyperbolic sine, the inverse hyperbolic cosine, and the inverse tangent 2 different ways. And that leaves 8 left. So if you want to do any of these as homework assignments, they're all very similar to the 4 that we did in this video, but they're equally as neat. Just remember one cool fact. Remember the inverse functions of things that are reciprocals of one another, like the inverse secant and the inverse cosine. If you put in reciprocal inputs into these, you get the same thing. Sort of like how the original functions are reciprocals of each other. If the inputs of these are reciprocals of each other, you get the same number. In other words, the inverse cosine of x is equal to the inverse secant of 1 over x. And that goes for any inverse cofunctions, hyperbolic or otherwise. So these should all be pretty easy to figure out on your own. Thank you for watching this video. We're going to be using a couple of the forms that I've derived in this video in the next video when we tackle the Universal Parabolic Constant. What the hectagon, man. Quick little thing, this channel has an Instagram, so it is at what the hectagon, of course, and it has a Twitter also. So this is Instagram, and of course this is Twitter, and it is of course naturally, also what the hectagon, at what the hectagon. Nope, at the hectagon. Oh, can't spell today. Okay, hectagon. And my email is the incorrectly spelled what the hectagon. Why spell check before you make the email, right? That you can't then change at gmail.com. Now all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. Along with other Instagram, Twitter, YouTube accounts that me and my friend Bill run. He does one for D&D. We together stream on Mixer under the moniker of Fredwood Live. So check the description for other stuff. This is just for my channel. This is my Instagram, at whatthehectagon, Twitter, at whatthehectagon, and email, at whatthehectagon, because I spelled it wrong when I made the email and now I can't change it. So that's the stuff. Thank you for watching, and bye-bye.